We now want to go through the reactions of different acid derivatives, and we are going to start with acid chlorides. Acid chlorides are the easiest of our acid derivatives to react. So they will react with any nucleophile to make just about any other acid derivative that any other acid derivative that we are trying to make. So we can have the nucleophile come in, react with the carbonyl compound, and in doing so, it will give HCl as a byproduct, or chloride in some cases it'll give as a byproduct. And then in practice, we typically are going to add something like a weak base, typically pyridine. Pyridine's good because even though it is somewhat nucleophilic, it's a really good leaving group once you make it a nucleophile. So pyridine is a good choice, and it helps to soak up any HCl that we might make. So that's the generalized reaction. Let's look more closely at some of the other reactions. So we can use oxygen nucleophiles. So we can either water, an alcohol, or a carboxylate. So if we use a carboxylate with an acid chloride, we can get the acid anhydride plus chloride would be our product there. If we react the acid chloride with water, we can get carboxylic acid plus HCl. This is where it comes into play that we would use pyridine. And if we use the alcohol with an acid chloride, we'll get an ester, again, pyridine, to soak up that HCl or neutralize that HCl. We can also use nitrogen nucleophiles. However, we end up having to use two equivalents of that nitrogen nucleophile. So if we're going to use something like an amine, a primary amine, a secondary amine, or just ammonia, we're going to end up using two equivalents of it, because one equivalent will be used to make the amide, and the other equivalent will be used to neutralize the leftover HCl. So one acts as the nucleophile, and the other reacts with the base to soak up that HCl byproduct. And we'll get an ammonium chloride of some sort, depending on which type of amine that we started with. All right. There are a number of different amide syntheses or compounds that are amides that we are interested in making. So we can take this meta methyl benzoyl chloride and treat it with diethylamine, and we can make the NN-diethyl metatoluamide, or toluamide, depending on how you want to say it. And this is the active ingredient in DEET. It has that very distinctive odor that smells like you've been camping. It's not a very pleasant smell, but it also it's not as bad as being bitten by mosquitoes, particularly mosquitoes with different kinds of pathogens in it. So it's a trade-off. Again, not very pleasant, but if you are susceptible to mosquitoes, then this is a pretty good alternative. And it has been shown to be pretty safe across a broad spectrum of different people. So both men, women, children, even expecting women. So the example mechanisms that we have with acid chloride. So the formation of anhydrides and carboxylic acids follow the same general mechanism. So here, if we've got a carboxylate, and that carboxylate reacts with our acid chloride, we will get, this is the first step in our mechanism, we'll form our tetrahedral intermediate, and that tetrahedral intermediate will lose the chloride, and when we lose the chloride, we will end up getting the anhydride. If we're going to do the formation of a carboxylic acid, that's going to require one extra step. So water comes in, reacts with the acid chloride to give us our tetrahedral intermediate. And before that chloride leaves, we need to deprotonate. And the thing we typically deprotonate with is the pyridine. And so we'll deprotonate with that. And then once we've done that, we can lose that chloride and we will end up getting the carboxylic acid. All right, let's look at number 11 on the in-class assignment. So here is number 11. Draw the products formed when benzoyl chloride, and I will start here by drawing benzoyl chloride. So it's just benzoic acid that has been converted into the acid chloride. So that is our starting material for all of these. In this case, we're going to use H2O and pyridine. So the pyridine is there to soak up the HCl. And so in the process of doing this, we are going to get benzoic acid plus the pyridinium chloride. So we'll get that pyridinium chloride. And that, again, that is, you have to have that pyridine in there if you want to make it work. Now, I'm hesitating whether I want to say this or not. I'm going to say this. If you put pyridine in with benzoyl chloride by itself, something kind of cool happens. I'm going to turn over the page and show you what happens. So, all right, so there is the benzoyl chloride. And so if we have pyridine, all right, that is ugly pyridine, but forgive me. All right, this will come in and react with that. And we'll get that tetrahedral intermediate. Oh, I need to kick those electrons out to the oxygen. So we'll have O minus, and we'll have a chloride attached, and we will have this. All right. So we'll have this. Oh, and that has a positive charge there. And that can lose the chloride. And when it does, we will end up with this. And here, let me go ahead and bring this down. All right, and so we will get this. This has a positive charge there. And then the chloride is still hanging out because of charge balance. That is what we get. This is actually as reactive and sometimes in some situations even more reactive than the chloride is. So we can form this as an intermediate. Now, most textbooks don't show this as an intermediate, but this does occur. There are some other reactions that can occur with this if we have more excess pyridine involved, but that's kind of cool. I'm sorry that my benzene ring here looks, or my pyridine ring looks a little lopsided there, but all right, enough of that. Let's go back to our problem. All right, so same starting material. So this starting material. And here we're going to have the CH3 COO minus, and that is the carboxylate. And so our product here is going to be that anhydride, and I'll put plus chloride. So whatever the counter ion of this was will become the counter ion of the chloride. Now, here we need excess of this because we need to absorb the HCl that is generated in the process of doing this. But when we use the NH3, we're going to end up getting benzamide. plus the NH4 plus and Cl minus. So ammonium chloride will be present. And then finally for this one, also excess. So the CH3 to NH. We'll get the NN dimethyl plus the CH3 to NH2 plus chloride. We'll get that dimethyl ammonium chloride as our byproduct there. Again, we have to use excess. We have to use at least 2 equivalents of these bases when we're reacting them with our benzoyl chloride. Otherwise, they won't go to completion. All right, so now we're going to look at reactions with anhydrides. And here with the anhydrides, anhydrides are not quite as reactive as acid chlorides, but they're still pretty reactive. And they will react with most nucleophiles. So here if we have a neutral nucleophile like this one, it comes in and reacts with this carbonyl, and these carbonyls are identical, so it doesn't matter which one it goes to. The other one will act as a leaving group, and then it will end up getting protonated in the course of deprotonating this. So we'll find that the nucleophilic attacks at one carbonyl group and the other carbonyl group ends up not getting used as an electrophile. It gets used as a leaving group. All right, when it comes to the reactions of anhydrides, we can't make acid chlorides with anhydrides. If you come up with a way to do it, let me know, but you can't really do that. And so the reason we can't really do that is that the conjugate base of that leaving group is the conjugate acid of that leaving group is a weaker acid than HCl. So that means this is a stronger base. So since this is a stronger base than Cl minus, we can't make the acid chlorides, but we can make the other things. So we can make all of the other acid derivatives. So we can make the carboxylic acids if we add water to it, and we'll actually get 2 equivalents of the carboxylic acid. If we react alcohol with it, we will get an ester plus the carboxylic acid. And if we react the amine with it, and again, we'll need 2 equivalents here. If we react the amine with it, we will get a primary amide and then the ammonium carboxylate, whatever the conjugate base of whatever this is. So we'll get that ammonium salt. All right, if we want to convert a anhydride into an amide, we can look at this mechanism. There are 3 steps. The first step, nucleophilic attack, then deprotonation, and then loss of our leaving group. So the first step, nucleophilic attack, we form our tetrahedral intermediate. You've seen this now, a tetrahedral intermediate, about approximately 100 times in the course of the last few chapters. All right. Before we can have this act as a leaving group, we do need to come in and deprotonate that intermediate. That gives us this, and then finally we can reform the carbonyl and lose this as a leaving group, and we will get that. So we'll lose that as a leaving group. All right. We can also make esters and amides. We can make esters and amides pretty easily using anhydrides. And so this is actually one of the syntheses that we do in my organic lab that I do with my students. We'll use acetic anhydride and salicylic acid to make acetylsalicylic acid. So we'll make this ester right there. And that works pretty well. Another ester that is fairly easy to make, or it's not an ester, it's an amide, is to make this, which is the acetaminophen. That is the active ingredient in Tylenol. Now, it is possible to make other drugs, and so some of those are not legal for you to make at your house. So I'm going to tell you don't do that. But if you take morphine and you treat it with acetic anhydride, you can convert it into heroin, which is actually more potent than the morphine was to begin with. It's also very dangerous and very easy to get addicted to. When they were first making it, they thought that they were making one that was less addictive than morphine. They were wrong. All right, we're going to look at number 14 on the in-class assignment. All right, so if acid anhydrides react like acid chlorides, which they do for the most part, with the nucleophiles described in chapter 17, draw the products formed when the following nucleophiles are reacted with benzoic anhydride. So I'm going to draw benzoic anhydride over here. You probably could figure this out. I'm going to draw the benzoic anhydride. All right, so there is benzoic anhydride. That's the one that we're interested in. If we use 2 equivalents of the Grignard reagent and then work it up with water and use the benzoic anhydride, we can get addition twice. And so we will get 2 of these Grignard. That one's only methyl, so we'll do methyl, methyl. And then when we use the water, it will protonate that alkoxide to give this alcohol. So the mechanism for this is exactly the same as the mechanism that I showed you back in chapter 17. With lithium aluminum hydride, it will definitely convert our anhydride into an alcohol. So lithium aluminum hydride is such a potent reducing agent. It goes all the way down to the primary alcohol. And then for this one is the lithium triterbutoxy aluminum hydride. It is the milder reducing agent that we found works with acid chlorides to convert them into aldehydes. Well, it will also convert our anhydrides into aldehydes. So we can form benzaldehyde. So we can get benzaldehyde. All right, so now let's look at reactions of carboxylic acids. We talked about carboxylic acids, that they are acidic back in chapter 19, the previous chapter. They typically have pKa's in the 3 to 5 range, closer to 5 for most of them. They can get below 4 if they have electron withdrawing groups or some other structural features that might make them more acidic. These nucleophiles are most nucleophiles that are also pretty strong bases, or at least a lot of the nucleophiles that we have looked at are pretty strong bases. So a lot of nucleophiles, when we put them with a carboxylic acid, it will deprotonate the carboxylic acid. Once it deprotonates that carboxylic acid, it makes this carboxylate salt, and it is not very reactive. And so you've gone from something that is decently reactive with nucleophiles to something that is not as reactive. So you've shut down the reactivity, or at least quite a bit of it. So how do we work around that? Well, there are a couple of tricks. If we want to convert it into an acid derivative, we can convert the carboxylic acid into an acid derivative with a couple of tricks. One is we can convert it into an acid chloride using thionyl chloride. And we will talk about that one here in just a few minutes. We can use heat on cyclic if we're going from a diacid to a cyclic anhydride, and we'll see that later in this section as well. If we have an alcohol with acid, we can do, this is called Fischer Esterification. We have a section that we're looking at on that coming up. And then it's possible to convert the carboxylic acids into amides as long as we're willing to do one of two things. one, put a lot of heat into it, or two, use a special reagent, and that special reagent is called dicyclohexyl carbodiamide, or DCC. I will show that to you in a minute, so you don't have to have that memorized just yet. But you can make amides in both of these directions. They each have their advantages. The top one has the advantage of when it works, it's pretty clean. The disadvantage, you have to go to a high temperature. This one has the advantage of you can do it at much lower temperature, it's much milder, but then the disadvantage of it is that sometimes separation from the byproduct of the DCC can be a little bit tricky. A little bit. All right, so if we want to convert a carboxylic acid into an acid chloride, we can't do it directly using chloride as a nucleophile. Chloride, while not very basic, is also just not that great of a nucleophile for nucleophilic acyl substitution. Because it is a weaker base than hydroxide, if we attempt to use the chloride directly, we will get a lot of nothing going on. So we have to use another compound that's called thionyl chloride, which is kind of a remarkable compound, very, very useful. And I think we've seen this one before when we were looking at converting alcohols to chlorides. I think we used that one before. But here is the reaction. We can convert a carboxylic acid into an acid chloride. Our byproducts are going to be sulfur dioxide. So, and just in case you're wondering, yes, you should do this one under a hood because this one stinks. And, well, so does the acid chloride. It stinks too. And so does the thionyl chloride for that matter. And, you know, the HCl doesn't do you any wonders either. So definitely all this should be done under a hood. So here is an example converting benzoic acid into benzoyl chloride using thionyl chloride. Easy to do. Easy to do. All right. Let's look very briefly at the mechanism. There are 4 key steps in this mechanism, and I show you this mechanism not so much because I want you to reproduce the mechanism, but instead I want you to understand why it works. I want you to understand why it works. So the 4 steps are, first thing is that the thionyl chloride will react with the carbonyl oxygen. So we'll get a pair of electrons, and you can either do it from the oxygen or from the pi bond, but that reacts with the sulfur, and we get this. We simultaneously have chloride leave from the thionyl chloride, so we'll get this. Well, this is a very weak base, or it's a very good leaving group, and it's a very weak base. The chloride will come along and deprotonate that H+, that's our second step. After it deprotonates, now chloride can come in and make our tetrahedral intermediate that we have seen approximately 102 times now. So it will make our tetrahedral intermediate, and we will simultaneously lose that leaving group, and it'll give us sulfur dioxide and chloride. Sulfur dioxide is a gas, so it'll just bubble right out of solution. And because it bubbles out of solution, it essentially makes this last step irreversible. So we don't have it going back. So we'll lose that. All right, and so that's how we get the acid chloride. Again, I'm not so concerned on you showing me the mechanism for this. I want you to understand what's going on. This first step, the whole point of it is to create something that's a better leaving group than water. We're converting the OH into a different leaving group, and we're making something that's a really, really good leaving group, which is this functional group. And it leaves in the form of SO2 and the chloride. How about converting a carboxylic acid into an acid anhydride? Well, it's very difficult. If you have a regular carboxylic acid and you're trying to convert this into an acid anhydride. So let's say you have benzoic acid and you're trying to convert it into benzoic anhydride. That is a little bit tricky. And the reason it's a little bit tricky is because in that there's a distinct increase in the entropy, and you usually have to do this at high temperature. And so things where we have an increase in entropy and you do it at high temperature, they tend not to work very well. So go back and look at your thermodynamics and see why. At high temperature, things that have a large positive delta S aren't going to work very well. Otherwise, just ignore my statement there. However, cyclic anhydrides don't have that issue. In fact, the heat helps because we haven't, I think I said that backwards. On the other ones, they have a decrease in entropy. They have a negative delta S. This one has a significant positive delta S. And because of that increase in entropy, we're going to be able to do this at high temperatures. So we heat it up to high temperatures, we'll lose H2O, and we'll end up getting the acid anhydride. We call this dehydration. We call this dehydration because we're losing H2O. And in fact, anytime we're making an acid anhydride, it's dehydration. What about converting our carboxylic acid into esters? Well, we can do it by a process that we call Fischer Esterification, invented by Fischer. All right. And so the way that this works, this is a common experiment that is done. In most organic chemistry labs as a basic reaction that you need to know. But you will take the carboxylic acid plus an alcohol, and you will put sulfuric acid in as a catalyst, and that sulfuric acid will make it so that you can create this ester, and you'll have H2O as a leaving group. This reaction is an equilibrium, so you can force the reaction one way or another using Le Chatelier's principle. If you remove water from your system, you can force this reaction to the right and create more of your ester. If you add water to the system, you can do hydrolysis, so you can convert the ester back into the carboxylic acid. We're actually going to do a mechanism for both of these. So we're going to draw out a mechanism for Fischer Esterification. That one's coming up here in a slide or two. And then shortly after that, when we get to the section on esters, we're going to convert the ester into a carboxylic acid and an alcohol by adding water to our mixture. Here are a couple of examples. So here, this is acetic acid and ethanol. Between these two, we can create ethyl acetate, and we will get water as a byproduct there. Here we've got benzoic acid and methanol. That will combine together to give us methyl benzoate and water. So these are fairly easy reactions to do, and both of these smell pretty good. I like the smell of esters. All right, let's look at Fischer Esterification mechanism. There are 6 steps. All right, it is acid catalyzed, so you can guess the first step is going to be protonation. Again, anytime you have something that is acid catalyzed, there's a pretty good bet that the first step is protonation. So we are going to protonate our carbonyl, and when we protonate that carbonyl, we will get a resonance stabilized cation. I don't have the other resonance structure here, but trust me, it exists. So we'll have a resonance stabilized carbocation. That increases the partial positive charge on the carbon. In other words, it makes the carbon more electrophilic. So the whole reason that we protonate it is that and then we use an acid catalyst, is that it makes the carbonyl carbon more electrophilic. Then we can have our not so strong nucleophile come in, which is just the alcohol. It reacts with the protonated carboxylic acid to give our tetrahedral intermediate. And again, we've seen this many, many times now. We'll use whatever the conjugate base of our acid was to deprotonate that intermediate, and that will give us this, which you'll see, this is an intermediate, and it's not particularly stable, but it does exist for short periods of time inside of our solution. This will get protonated by our acid, and it doesn't matter which OH gets protonated, because they're both going to get protonated at one, either one or the other is going to get protonated. In fact, the OR gets protonated sometimes and it goes back, but we can protonate this, and when we do, that creates a really good leaving group, and that really good leaving group is H2O. When we have that leaving group leave, we'll create this carbocation, which is resonance stabilized, but I don't have the other resonance structure. We deprotonate, and when we deprotonate, we will get the ester. All right, this is one of those mechanisms I want you to know, and most organic chemistry professors are going to want you to know this mechanism. All right, one quick note about esterification. It does not work with base. If you attempt to do esterification with base, you're going to have a bad day. And let me explain why. As soon as you put a base in with the carboxylic acid, it's going to deprotonate that carboxylic acid and convert it into the carboxylate salt. That carboxylate salt is not very reactive, at least as far as substitution goes. So you're not going to be able to do the next step of the reaction, which is to go, to create all those intermediates and get to your product. So the base removes a proton and deactivates your carbonyl. So as much as adding a proton to this will increase the reactivity of the carbonyl, deprotonating this will decrease it and make it so it's unreactive. All right, let's talk about intramolecular Fischer esterification. It is possible, if you have a gamma or delta hydroxycarboxylic acid, to form either a 5 or 6 membered ring. If it is gamma, you will form a 5-membered ring. If it is delta, you will form a 6-membered ring. I encourage you, when you're doing these problems, and we're about to do one, we're about to do a mechanism, I encourage you to label your carbons. So label them so that you can identify which carbon is going where, so that you know what's going to happen. All right, so here we've got, this is a gamma hydroxycarboxylic acid, and because it's a gamma, we can form a gamma lactone, which is a 5-membered ring. This one is a delta, if we count 1, 2, 3, 4, so alpha, beta, gamma, delta. That's a delta, so we're going to get a 6-membered ring, which is the delta lactone. All right, get ready for a mechanism. All right, you want to get comfortable when you're about to do this mechanism. So you want to get comfortable. Make sure that you have plenty of space. I've tried to put enough space on this paper, but if you're just following along at home, you'll want to make sure you have plenty of space. All right, first things first. We're going to turn this into this. And so let's label our carbons so that we're clear of where everything is. So we're going to call that carbon 1, 2, 3, 4, 5, and then there's the oxygen. That oxygen is going to become this oxygen over here. As far as what carbons there are here, this is 1, 2, 3, 4, 5, and then there is our oxygen. We are going to lose water. The water we're going to lose is this OH here. It'll get protonated and we'll lose it. Actually, it'll be one of those, and we don't know which one it's going to be, but it doesn't really matter. One of them will get lost. All right, and let's get started. So, very first step, we've got an acid catalyst, and the very first step, anytime you have an acid catalyst, protonate. I'm going to choose a different color here. So we're going to take HOSO3H, and we're going to take that carbonyl oxygen there, and it has some lone pairs on it, and we're going to go from that lone pair to this hydrogen and deprotonate this sulfuric acid. All right, so we deprotonate that sulfuric acid, and then when we do that, deprotonate that sulfuric acid. When we do that, that's going to give us our protonated carbonyl. So not much has changed here. All right, so we'll have a positive charge there, OH. All right, now there is an additional resonance structure. Go ahead and draw this there because we're going to need that in a minute. There is an additional resonance structure, which I am going to draw. Remember, resonance structures have this kind of double arrow in between them. All right. And excuse me for a second. I'm going to go back a little bit so we can get the whole mechanism all at once here. All right, there we go. Hopefully we get that all in there at once. All right, so we're going to take this pair of electrons that is the pi bond, and we're going to kick it out to the oxygen, and that's going to put a positive charge on this carbon. So HO. All right, and oh, I forgot these things on carbon 2. All right, so now we're going to take one of the lone pairs of electrons that is on our alcohol, and we're going to attack that carbon. OH, OH. So those are both there. We'll have a positive charge here. And we still have these methyls there. And I'm going to go ahead and label so that we're consistent with the numbering up here. 1, 2, 3, 4, 5 carbons. That way you know which ones we're talking about. It's still the same ones we had there. All right. Go back a little bit further. It's really nice to have the whole mechanism at once. All right, so now we're going to use the conjugate base of our acid. So when we did this, we created the hydrogen sulfate ion. We're now going to take that hydrogen sulfate ion, the OSO3H minus, and we're going to deprotonate this. So we'll go here, and we'll deprotonate that. That's an oxygen. All right. Now, these have lone pairs of electrons, and so we're going to need to protonate one of those. It doesn't matter which one we pick. They're identical. There's no difference between the two, so I'm just going to pick that one that's on the left for fun. Okay. And we're going to protonate it with sulfuric acid again. So HOSO3H. We'll go from that pair of electrons to that hydrogen. We'll kick this pair of electrons to that oxygen. And that is going to create again, I kind of made that ugly. All right, here, I'm going to pause for a second. All right, I paused for a second to make these oxygens more beautiful. And now let's go ahead and put OH there and OH2 plus there. Now we're going to have that H2O act as a leaving group. So we're going to have that act as a leaving group. And when it acts as a leaving group, that's going to create a carbocation. That carbocation is going to be resonance stabilized. I clearly didn't leave enough room here, but so let's create that resonance stabilized carbocation. So positive charge there. Oxygen, hydrogen, there's lone pair electrons here, and there are lone pair electrons there, but I'm going to mostly be concerned with the ones that are up here. We'll go ahead and put those methyls on there. So we've lost water now, and now we're going to take one of these pairs of electrons, and make a pi bond there. And so now this is where I've really gone off the rails here as far as our resonance structures. Positive charge there. We still have lone pair electrons there, but they're not super important. I mean, they contribute to the overall resonance structure. I could draw another one, but I'm not going to. I'm going to stick with this because we're going to, oh my goodness, I just put that OH onto another page. All right, the dangers of working with multiple pages here. All right, so now we're going to deprotonate that OH. So, and when we do that, it will make this. The thing we're going to deprotonate it with is the conjugate base of sulfuric acid, which is this hydrogen sulfate ion. It has a negative charge there. We're going to go from that oxygen pick up that hydrogen, and then we'll kick that pair of electrons to the oxygen. Sorry this got so scrunched. I have all this extra room that I didn't use wisely. I forgive myself. But when we do that, we're going to get this. That's our product. And that is our stepwise mechanism. That is our stepwise mechanism for doing Fischer esterification. So just a reminder, the steps: protonate. All right. And then we can do the resonance structures, but it's protonate, our next step. Nucleophile attacks. All right. Then deprotonate. Protonate again. So here we protonate the OH. H2O acts as a leaving group to create our resonance stabilized carbocation, and then deprotonate. So protonate, nucleophilic attack, deprotonate, protonate, lose leaving group, deprotonate up here. Those are all the steps. Practice that. Don't just practice this one. Go pick another one and practice it. And if you're looking for another one, just like take the methyls off and just do it with a simpler one. All right. What if we want to convert a carboxylic acid into an amide? Well, that is definitely possible. We can convert carboxylic acids into amides. However, when we take a carboxylic acid and react it with some sort of amine, the very first thing that's going to occur is that we will get an acid-base reaction between the amine and the carboxylic acid, and that will give us this ammonium carboxylate. So it'll give us this ammonium carboxylate. If this were acetic acid, this would be ammonium acetate, which is a very common reagent. All right, so there we have this ammonium carboxylate. That ammonium carboxylate, you could put that in a jar and leave it there for 20 years, and it will be pretty stable as long as it stays at reasonable temperatures and it's not exposed to too much moisture, and you don't spit on it or anything like that. You don't throw acid or base in it. It'll be stable for a long, long time. However, if we take it and heat it up, and by heat it up, we need to heat it up to a high enough temperature that we can drive off H2O. So ideally, we need to heat it up over 100 degrees Celsius, because as you know, 100 degrees Celsius is the boiling point of H2O. And if you get it up that high, you will start to drive off H2O. And when you do that, you will get an amide. Now, that's pretty harsh conditions. That's not easy conditions to do. So room temperature, nothing happens. But if you heat it up over 100 degrees Celsius, you can dehydrate. And here, this is an example. So here we've got benzoic acid with just plain ammonia. We put them together and we're going to get ammonium benzoate. But once we heat it up, that ammonium benzoate will do a reaction where we will get benzamide plus H2O. All right. You can do it with this particular carboxylic acid and this amine. You'll probably need a sealed container to contain all the amine at the high temperatures. This is not a trivial reaction to do. This is something that you need a little bit of engineering to make sure that you don't have your vessel blow up because of high pressure. So not a trivial thing to do, but once you know how to do it, you can do it on huge scales, and it works pretty well. All right, what if you've got a reagent that won't stand up to that kind of temperature? There are a lot of compounds that will start to decompose at temperatures well below 100 degrees Celsius. So you can react a carboxylic acid and an amine directly using an additional reagent that's called dicyclohexyl carbodiimide. So dicyclohexyl carbodiimide. This is a diimide. So this is a diimide functional group right here, and this is the dicyclohexyl. So DCC we call it for short, and we call this a DCC coupling. That's typically how we will refer to this. So we can treat carboxylic acid with our amine, and there is our DCC. When we do it, we will produce our amide, and we will produce a side product that is called dicyclohexylurea, or DCU is what I usually call it when I put that in my when I would put it in my notebook. Right? This reaction works great. You can do it at room temperature. You don't have to heat up your hard worked on amines or carboxylic acid. So it's pretty versatile. And as I mentioned, you can do it at room temperature. Really, the only negative sides to this, all right, everything has to dissolve in methylene chloride, which that's not too hard because most organic things will dissolve in ethylene chloride, or not methylene chloride, dichloromethane, DCM, so dichloromethane. And this product is not very soluble in dichloromethane, so you will get this coming out of solution as a solid, right? And so once you're done with the reaction, you can filter it, and you'll have mostly your amide and whatever, your dichloromethane solvent left over. So you won't have any of this, and this can be filtered out mostly. There usually is a little bit of that dicyclohexylurea left over, and so sometimes you'll have to do some chromatography or something else to isolate your amide. But it is an effective method for making these amides. All right. And again, it just gives you another choice. Anytime we're trying to do reactions, it's good to have alternatives that will give us the same result but under different conditions in case, heating it up to 100 degrees doesn't work for your original reaction. All right, let's look at the DCC coupling mechanism. I am not going to write it out, and I'm not going to force you to do it on a test. Now, your professor, if somebody from a different class is watching this, your professor may want you to do the DCC coupling mechanism. And if they do, good for them. But the main thing I want you to understand is why it works, what's going on. So 5-step mechanism. First step, we're going to deprotonate our carboxylic acid with the DCC, the dicyclohexyl. My brain just stopped for a second. Let me say it again. Dicyclohexyl carbodiamide. All right, so the DCC is going to deprotonate our carboxylic acid. And so now we've got this hydrogen bonded to the nitrogen, and we've got this carboxylate. That carboxylate is going to act as a nucleophile to attack the carbon on the DCC. And when it does, we'll now get this new bond, and that new bond is going to make this carbon is more electrophilic now. So now we're going to have a nucleophilic attack by our amine on the carbonyl carbon. And when we do, we create our favorite tetrahedral intermediate that we've seen a gazillion times. This next step we're going to call proton transfer. It's actually 2 steps, right? We have to deprotonate this NH3 plus, or this NH2 plus. There's an R group there. So we have to deprotonate that, and then we protonate this other nitrogen. So it's technically 2 steps there, but all right, we're not gonna split hairs over that. And then our final step is, once we've done this, we're going to have our carbonyl reformed. So we're going to form our carbon-oxygen pi bond. We're going to have the DCU, the dicyclohexylurea, act as a leaving group. And then we'll kick this pair of electrons out to the nitrogen, and there is our DCU. There's our DCU, and there is our amide that we made. So we lose that leaving group. Again, the goal of this is not for you to memorize this mechanism. The goal is for you to understand what's going on. We're going to make this carbon electrophilic, which happens here, and then we're going to make this carbon electrophilic. So then when we do the next step. All right, let's go to number 19. This is a short problem. What is the final product when acetic acid, and I'm going to go ahead and draw acetic acid here. All right, that's not very pretty, but there you go. So that's acetic acid, and we're going to react it with each of these reagents. We'll start with methylamine. And so when we react that with methylamine, and I'll try to be a little bit neater here, we're going to get the carboxylate, because this is going to deprotonate that carboxylic acid. So the methylamine is going to deprotonate that, and then we'll have CH3NH3+. And so this will be a salt, and you could put that salt in a jar and leave it there for a long time, and it will still be stable. All right, so that is the reaction that occurs at room temperature. If we heat it up, and when we heat it up, we're really saying heat it up over 100 degrees Celsius. And we heat it up to 100 degrees Celsius, and we will get the CH3 carbonyl nitrogen, and then there is a methyl on that nitrogen and hydrogen, and we'll also get H2O. All right. If we do this with DCC, so we're going to get the same product. So we get the CH3 carbonyl NH CH3, but we're also going to get the dicyclohexylurea, which I'm going to go ahead and draw because, I mean, isn't it fun to draw this? All right. And so nitrogen, hydrogen, carbonyl, nitrogen, hydrogen, and then a dicyclohexyl. There's the other cyclohexyl. All right, and so this is our dicyclohexyl urea, and urea is just, if you have replaced those two cyclohexyl groups with hydrogens, that's urea, and so this is dicyclohexyl urea. And again, the whole driving force behind this is the formation of this. This is pretty stable, and it's not soluble in dichloromethane, so it just sort of falls out of solution while this stays in solution. It's really kind of an elegant reaction. I love doing this reaction. Not a reaction that we typically do in an undergraduate organic class, but pretty cool reaction. Well, we are at 52 minutes here, so I'm going to stop this video, and the next video is going to start with section 10 and talking about reactions with esters.